intéressé dans au recording in progress, justement de la déformation au Chili. Okay, so during all my talk, I will focus on subduction zones that are a kind of a plate boundary, convergence plate boundary. So you have here in different color the different subduction zones we have on Earth. So just before dive into more details, let's go back to some basics. So a subduction zone, you have a lithosphere here that plunges beneath another lithosphere. The two lithospheres lie above the asthenosphere, so it is the shallower part of the upper mantle. And in between here, because these two plates are locked, you have big earthquakes here. But the earthquake that occurs here represents only a short period of the life of the fault. And we can divide this life in three different parts. The first one is the inter-seismic phase, where the subduction interface is locked for a very long period, very long time. So, for example, 100 years, could be 1,000 of years. And during this period, you accumulate elastic deformation, that's a potential energy for future earthquake. And then suddenly the earthquake, so what we call the co-seismic phase, from second to minutes in terms of duration. And it is a sudden release of all this accumulated elastic deformation through time. And then you have the post-seismic phase, which can last for years to 100 years. And there are three main physical processes that are playing their role in the post-seismic phase. The first is the poor elastic rebound that has an impact in a very near field close to the trench, which is a rebalancing of pore pressure. Then you have the after slip, which is a slip on the subduction interface, and then the viscoelastic relaxation of the asthenosphere, and that can induce deformation very far away from the subduction trench, 100 kilometers, 200 kilometers, and it is the physical processes I will focus on this during this presentation. So the seismic cycle is the repeating of co-seismic, post-seismic, and inter-seismic phases through time. And we can measure these different parts of the seismic cycle using, for example, GPS. So we have here our GPS station on the continental lithosphere. And here you have the GPS time series that is expressed in the overriding plate reference. So the inter-seismic period of the seismic cycle is characterized by a linear displacement, the co-seismic by an offset, and then the post-seismic deformation with a transient displacement. And so these different phases of the seismic cycle are very well measured with GPS, and we have very different characteristic motions. So linear trend, an offset, and transient displacement. So how we estimate these quantities in GPS time series? So you have an example here for two GPS stations facing the Heliapel 2015 earthquake. So this station is in the near field and this station is in the far field. For this station, you have a high signal noise ratio. So it means it's quite easy to estimate a co-seismic offset. And when you are far from the trench, or more than 1,000 kilometers, it starts to be a little bit tricky, and you have to estimate, for example, here some trends or some numerical tricks to estimate this offset. And you have the exact same thing for the cumulative post-seismic displacements. When you are close to the trench, it's quite easy to estimate the amount of displacement since the earthquake at a given time. But when you are far from the earthquakes, it is by far more complicated. So we need a dense GPS networks to monitor the deformation of the whole lithosphere, of the whole continental lithosphere. And this is the kind of pattern we expect through the seismic cycle for large-scale deformation. So here we are in Japan, 6 months after the two earthquakes, and all the displacements are oriented toward the subduction trench. You have this example in Chile, 40 years after the Valdivia earthquake, which is today the largest earthquake recorded on Earth. You have a pattern that is more complex. You have a landward motion close to the trench, and you have seaward motion when you are further inland. And finally, the Cascadia example, we are 300 years after the earthquakes, and this time all the plate is moving landward. So we have different kind of deformation pattern through time, very different from the early post-seismic, only 6 months, to the late inter-seismic, 300 years later. So the question is, how can we model this different stage in the deformation? So we use what we call rheological models. So rheology is the link between the stress, so the force you apply on the material, and its response, so the deformation of its material. And the more commonly used rheological model is the elastic model for modeling, for example, the post-seismic phase, the earthquake. And here, when we apply a stress in an elastic material, you have a sudden elastic deformation, and then you have a new long-term motion. You have no more deformation after you impose your stress. Viscoelastic rheology, you add to this elastic spring here a dashpot that models the uniform and long-term motion here. So this is what we call the Maxwell model. And we can build more and more complex viscous model, for example, the Burger's model, which is a Maxwell model with a Kelvin Voigt viscous model. And adding this part in the model had a transient motion here to the previous uniform and long-term motion we had. And following this, first, you have two parameters here. This one controls the amplitude of the transient motion, and this one controls the duration of the transient motion. And following this rule, we can build more and more complex viscous rheologies. So here is what we can call the two Burgers model, or extended Burgers, where you had another transient motion. So here we have two Kelvin Voigt model, and we have here two transient motion. And following the same rule, you can build more and more complex rheologies. So to model the post-seismic phase, the long-term motion, we use viscoelastic models. Viscoelasticity, post-seismic relaxation is characterized by non-negligible far-field post-seismic deformation. So we are here in Argentina, very far away from the Maule earthquake in 2010 in Chile. And we clearly see here that even we are far from the trench, we measure a non-negligible deformation, 1.5 centimeter of displacement. And we model this deformation using viscoelastic models, in that case, Burger's rheology. For the inter-seismic, we use elastic models to model this deformation. And we are using what we call the coupling argument, the coupling distribution here. So the coupling is basically how much the fault is locked to produce the deformation you measure at the surface. What is the state of slipping along the subduction interface? So when you have red colors, it means the fault is entirely blocked, and so you accumulate elastic deformation. And when you have like a white value here, it means your fault plane is creeping. You do not accumulate any deformation. And coupling works very well in that sense that we have a strongly agreement between recent earthquakes. So here it's the Illapel 2015 earthquake in Chile, and the rupture zone we are inverting on the fault plane. The problem of elastic models to model the inter-seismic phase of the seismic cycle is that if we assume that we are in a two-plate regime, we have at the end a strong residual here in the midfield. So we are between 300 kilometers to 500 kilometers through the trench. You see here that this distribution of coupling induces here a very high residual and a coherent residual. And so elastic models in that case requires another plate, a third plate, to diminish this residual. And this is what we call like a sliver. Other people use the term of the other physical processes that we call underplating. So we need another hypothesis to explain this midfield deformation. Here you have another example in Sumatra after the 2004 earthquake. So here you have the inter-seismic deformation. So we are before the 2004 earthquake. And you see that when you are modeling this inter-seismic, so in green you have the GPS data that are along this profile here. And in black you have the model from an elastic rheology, and in blue and in red from viscoelastic rheology. And we clearly see that there is a good agreement here in near field between the two models, viscoelastic and elastic. But when it comes to far field, elastic model does not predict any more deformation, where it is the case for the viscoelastic model. So the goal of my presentation is to show you how can we model the inter-seismic using viscoelastic models, and I will also talk about the post-seismic motion. And we can summarize this presentation with these two questions. The first one is how to model the slip on the subduction interface to reproduce here the current GPS deformation measured, the current deformation measured with the GPS. And the other question is, which mechanical model do we need in the asthenosphere to make the link between what is occurring here and what we are observing here? So before to dive in these two questions, first one is where are we conducting this study? What kind of data we are using and what kind of model we are using? So my work focuses mainly on the Chilean subduction zone. So where you have the convergence of these two plates, the Nazca plate beneath the South America plate, at a convergence rate about 6.8 centimeter per year. This is a very active region in terms of seismicity. You have here through time the moment magnitude, and you see that we have 12 events that are higher than magnitude 8, so 12 megathrust earthquakes. In particular, between 2010 and 2015, you have 3 megathrust earthquakes in 2010, Maule earthquake, 8.8, 2014, the Iquique earthquake, 8.1, and in 2015, the 8.3 earthquake here. And the thing that is really interesting with the Chilean subduction zone is that we have different segments of the subduction zone that are at different stages of the seismic cycle, and we can measure these different stages using geodesy. So the data I'm using are from Émilie Klein and Christophe Vigny at ENS. So I will show you in this presentation only a continuous GPS station, but I'm also using a survey GPS station when it's needed. So you have here a map of all the stations we are processing at ENS. An example here of a permanent station from ENS here at the north of La Serena. And you can find all the data now in the geodesy plotter in the Formatter network. So you can download all the time series I will present you today following this link. And the model I'm using, so I'm using finite element model of the Chilean subduction zone. So you have here the different geophysical regions I have in my model. And in particular, the dip of the slab, so the pending, follows the slab 2.0 model all along the Chilean subduction zone. So you have here different stages that we that are needed to recreate this model. So we start from 2D cross section, and then we extrude this problem in 3D. We deform the surface of the slab to match it to slab 2.0. We incorporate this slab into a bounding box, and then we recreate the different geophysical region using a knife. We are cutting the different depth using some planes. And so you can find this mesh in Zenodo. There is also a Git. I think it's, I will show you later, but we try to create like a platform for others to work on it. All the people that are interested in deformation in South America, in large scale deformation in South America, can use this model, and we can compare all our different, for example, co-seismic sources, or and the deformation they are inducing. So a question that is relevant is, why do we need another model? Why to write a paper about a model at the end? Because there are lots of finite elements models that are existing today. So some of them are not in Chile, but it's something that is very common in the literature, in all different studies. You have some examples here that have developed their own finite element model. The problem in all these models is that some of them are not in 3D, and we need 3D mesh and spherical mesh because we are looking at deformation very far away from the trench, thousands of kilometers from the trench. So sphericity plays here a role. We need a large bounding box, and I will show you just after why, because we need them. You have some models where you have only 500 that are only 500 kilometer depth, and I will show you later that it can be a problem when you try to model the deformation over a very large scale and over a very large long period of time. And then you have some 3D finite element mesh, for example, this one here from the work of Emily, but there is only one slab geometry in all the mesh. And in Chile, for example, we need this variation in the slab dip, because we have here, for example, like flat slab. So to explore the role of these different features, we need to incorporate them into our model. So why is it a problem when you have a low bounding box? So when you have a mesh that is only 500 kilometer depth, and when you are looking at deformation thousands of kilometers from the trench. So here is the reason. So it's a test where we are playing with the depth of the finite element mesh, and we are also playing with the boundary conditions we are applying at the bottom of the mesh here. So here it's the reference mesh, is a Chile mesh 1.0. And here you have a version that is truncated at 270 kilometer depth. And what I'm showing you here is, as function to distance to the trench, the post-over-co ratio. So it's the cumulative post-seismic displacement normalized by the co-seismic offset. It's quite a good quantity to observe both co-seismic and post-seismic deformation agreement with this model. So in gray here you have the line that is come from this model, and in red you have using this truncated mesh what we get. So we see that in very near field we have a good coherence between all these models. But when we are farther than 400 kilometers from the trench, we see that the truncated meshes diverge completely from the reference. So this is a problem. It means that the size of your model has an impact on the modeling you are doing, and this is a real problem. We can increase the size of the mesh. So we had here, so you have the asthenosphere in yellow here, and we had a portion of upper mantle that is elastic. And we see that when you increase the size of your mesh, you increase the agreement with the reference mesh you have here. And we can also doing something that is really commonly done by lots of studies, is to have an asthenosphere that is down to the bottom of the mesh. So like the first model, you see that the low viscous zone is from the base of the lithosphere down to the model. And even if your mesh is larger, having these low viscous zones until the bottom of the mesh is a problem, because you see here that depending on the bottom boundary condition you are applying, you have divergence between the reference mesh. So all these tests show us that we need this kind of mesh and not this kind of mesh to accurately model the deformation far from the trench at thousands of kilometers and for a very long time period. And we can also make the same exercise for the lateral extent of the mesh. When you have the full extent mesh is 5,000 kilometers in gray. We are reducing here the mesh at 1,500 kilometers. Let's say, I mean, it's okay to look at deformation at only 1,000 kilometers from the trench. If I have a mesh like that, it's okay. But when you look at it, you see that it's not the case. You have a divergence from your larger model. So it means that the size of your model have an impact on your modeling deformation, and that's a real problem. And you see that you have also the same impact, but with I would say it's with a lower magnitude when you reduce the mesh in the oceanic side. But because we are looking at deformation in the continental part of the South America, it's something that can be done. So we are in Chile, we have data, we have GPS data, we have model. Then how to model the slip? The first question, how to model the slip on the subduction interface. So the question is simple: what history of slip, what slip on the interface, what earthquake history do we need here to reproduce the deformation field we are measuring today with GPS? So to do that, we are using the backslip theory, which is very loudly used. The backslip theory says that the deformation that is due to a locked interface is only induced by a supplementary slip on a locked portion of the subduction interface at the scale of the seismic cycle. So I'm explaining you what it means. So you have here, through time, the slip that occurs on the megathrust. So you have big earthquake, you have a lower earthquake, so magnitude 9, magnitude 7, 7.7. And we can decompose this slip on the interface using the plate convergence. So you assume that there is no deformation induced by the plate convergence, and what we call the supplementary term, supplementary slip, which induce deformation. And another important point of the backslip theory says that in the long term, the supplementary slip must average on a zero value. So you mean on the long term, you must have a zero average value of slip. So here it's a real story. Let's say that it's a real story. So you have the time since the last earthquake. So let's say that the earthquake here, the last earthquake, occurred at time 0. When we are looking into the past, we see that 200 years ago, there was a magnitude 8.8 and the magnitude 9.1, 9.2, etc. And today, this what is here in red show you what we are measuring with GPS. We are measuring this, because geodesy is in real time, we are measuring this slip on the interface. This is a coupling we are measuring. So how to model this supplementary slip? Because we have maybe in some region quite a good knowledge of the seismic history, but when it comes to the past, it starts to be very difficult to constrain. The first way is to use elastic model, what we are all doing when we are inverting a coupling map. We are assuming that the earthquakes that occur in the past do not have any impact on the current deformation. Only the real time matters, that would say. So it's like you have a zero slip on the interface through time, and then it starts suddenly to slip at the moment you are looking at the data. The other way that is very used by the community when it comes this time to viscoelastic models, not elastic, it's what we call the long-term viscoelastic model or steady state. They assume that you have a uniform slip rate on the interface. So your interface is slipping for 10,000 years ago, so something like that. The problem from this hypothesis is that your slip is non-zero in average in that case, your supplementary slip. And finally, there is this way to model the seismic cycle using a regular cyclic history of slip on the interface. So you assume that the magnitude of the earthquake you are using is what we have really measured in the data. And the time between this earthquake, it's a time you can, if you have seismic history, if you have records of seismic history, you can constrain this time, or if you have not, you can estimate it at least. So this model takes into account the fact that the present day deformation of your overriding plate is as the memory of past earthquakes that occurred on the subduction interface. And why past earthquakes have an impact on the present day deformation. So here you have time, and you have here the displacement of, let's say, of a point located at the surface of the continental lithosphere. And we are here at this time, right before the earthquake. So at, let's say, 150 years ago, an earthquake occurred, and we are at this time seeing this displacement with GPS. And if another earthquake occurred here, we add this deformation. So at this time, the deformation displacement is the sum of this one and this one. And this is the cumulative curve that you are seeing here. And we have the right to sum these different curves, and it comes from results that I will show you briefly later that say that in the asthenosphere, the viscous flow is linear. So you can sum all these processes. And go back in time, you can do this thing to converge at the end with this green, dark green line here, where you have accumulated all the earthquakes that occur. And of course, the impact on the present day deformation, a recent earthquake has a more impact, has a bigger impact on the present day deformation rather than an earthquake that occurred 500 years ago. So the present day deformation is a sum of deformation due to past earthquakes that we call the superposition principle. Here, I show you what are the differences in terms of inter-seismic deformation for the Maole segment of the Chilean subduction zone when we compare these three models. So you have the elastic model in blue, the orange model that is the steady state, the long term, and in red you have the cyclic, the regular history of earthquakes. So when we are looking at near field deformation, we see that there is a good agreement between all these models. It means that when we are using our coupling models, we are not making a strong mistake in near field. So, okay, coupling model works. It's good to know. But when we are looking at very far away from the trench, so here we are in Argentina, you see that elastic models do not predict any more deformation, or the deformation is very, very low. And in comparison, the orange model you have here, so the steady state, predicts by far larger deformation rather than the regular cyclic of earthquakes here. And if we compare here, so using this profile, we compare the different velocities, inter-seismic velocities, compared to the realistic model. So in black, it's the input of the model is something that is not regular when you have magnitude 8.5, 9.1, 9.3, but around magnitude 9. And with and you see that the cyclic slip, the cyclic history reproduces very well the long-term, the real story of slip along the interface, where in orange here, you do not account for past earthquake. You are simply assume that your model, that you are slipping for a very long time, and you are far from this model. You have you are at 4 millimeter, 8 millimeter, so you have 4 millimeter per year of difference, which is very large, given the precision, for example, of the GPS, which is 1 millimeter per year. So we can discriminate these models. So the physics that is behind the cyclic slip is more realistic and produces a realistic amplitude of deformation compared to a realistic model one. So now we know how to model the slip along the subduction interface. And the other question is, what kind of, what is a rheological model do we need in the asthenosphere to make the link between what is occurring on the subduction plane and the GPS deformation? So here you have an example before the Maule earthquake. So the Maule earthquake is here, 2010, and we are before the Maule earthquake, before 2010. So these velocities here, GPS velocities, are expressed in the South American reference frame between 2000 and 2010. And here we have the Valdivia earthquake that occurred in the 60s here. So we want to, the idea is to how can we reproduce this data using these models. So first we are considering only the Maule segment of the subduction zone. For that, we will assume our regular history of slip to be a magnitude 8.9 every 150 years. If we assume a convergence rate of 68 millimeter per year, it gives you this magnitude every 150 years. To model the deformation, we are using this viscous model. So this is a very known model in the community, like we call the Weinberger's model, for the one I show you at the beginning of the presentation. And the parameters I'm using here comes from the study from Émilie Klein. And she used for this study 5 years of post-seismic deformation after Maule, and it was her best model from this study. So I'm using this rheology now. And I'm showing you how the plate, given this rheology, I'm showing you how the plate deformation evolves through time. So here we are facing the Maule segment. So we have two different color scales for larger displacement, larger velocities. So we are here 3 years after the earthquakes, and we see that displacement is oriented, the deformation of the overriding plate is oriented toward, mainly toward the trench. 5 years later, we see that this displacement decreases, and when we are at the end of the cycle, 150 years later, so we assume that we are at the eve of the next earthquake, we are in the inter-seismic period, all the displacement, all the plate is moving landward and no more seaward, no more seaward motion. But this deformation was for only one segment, the Maule segment. But you have here another segment and here another one. So let's have these two other segments. So for the Valdivia earthquake, so here the Patagonia segment, I will consider a magnitude 9.5 every 1,000 years. And at the north here, I will consider a magnitude 8.5 every 80 years. And so we sum, the sum of all these desynchronized cycles is allowed also using the fact that the viscous flow in the asthenosphere is linear, and this comes from the fact that when you normalize the post-seismic displacement by the co-seismic offset, you see that all this ratio, that is post-overgo ratio, follow the same curve, even if there is a huge gap in terms of energy release between a magnitude 8.9 and a magnitude 8.1. So this is the deformation we have before Maoli earthquake, taking into account these three segments. And so, okay, we have an orientation that is, we have a like kind of rotation that we also observe in the data, but we have two large deformation. That it means that in our model here, the long-term deformation, the viscosity that controls the long-term deformation is too low. We need to increase this viscosity. So this is why we are introducing called two burgers model. So because this viscosity, this long-term viscosity is too low, it is now a transient viscosity because we need this viscosity to explain the deformation right after the Maoli earthquake for a period of time of a couple of years. And here we have one order of magnitude viscosity that is one order of magnitude higher now. So 10 to 19 instead of 10 to 18. And so this time, this is in red, the kind of deformation you have in 2010 before the Maoli earthquake. So this time we have the good magnitude of velocities, but we see that we have still a bad orientation of all our vectors. We have something in common between, if we compute the residual maps, we will see a residual that is oriented this way. So at this stage, we have a realistic amplitude of velocities, but the orientation is bad. And just by playing with, for example, the magnitude of the last earthquake here, so we understand that there is this strong rotation that is oriented here before the Maoli earthquake due to the fact that in the 60s, you have here the 9.5 Valdivia earthquake that push toward the trench all the deformation of the plate. So this is this movement we are seeing here. And simply by reducing the magnitude of the earthquake, so 9.4 instead of 9.5, we see here that we have a better orientation of our vectors compared to the data. So what I am saying here, it's not that Valdivia, maybe it's 9.4 instead of 9.5. It's something that is debated, but I'm just saying that with this kind of models, these kind of models are very powerful to explore what occurred in the past. For example, the return time of the earthquake, the magnitude of the earthquake, and maybe we can constrain better this seismic history using this kind of model. So rapidly I give you a bonus section, like revisiting the inter-seismic definition. So what can we learn from the inter-seismic, our current view of the inter-seismic definition using these viscoelastic models? So the co-seismic part of the seismic cycle is very well defined. It's the earthquakes. It lasts seconds to minutes. But then the transition between post-seismic and inter-seismic is not very clear, actually. You have the inter-seismic that we are now assuming all that like a steady state. So it's a steady state deformation. You have your earthquake, the co-seismic part, followed by post-seismic, which is composed of afterslip, viscoelastic relaxation. And at the end, you also expect a steady state period, so the seismic period, but in between, when we decide we are no more in this regime, but we are in this one. And we have some natural evidence that we do not have retrieve, we are actually not in the inter-seismic phase for numerous segments of the Peru-Chilean subduction zone. So you have here this very nice figure from Bertrand Lovry that show you that the velocity you measure before the Arequipa earthquake in southern Peru here is different from the velocity you have here today between 2013 and 2022. So it means that we have not reached yet the this inter-seismic motion we had before the Arequipa earthquakes. And I have done the same exercise here using Antuco station facing the Maule earthquake, where we see that 15 years after the earthquake, we did not retrieve, we do not have the same velocity. So it means we are not in the inter-seismic period. And the same exercise here for Hillapel earthquake, 10 years after, we do not have the same velocity, even if we are closer. So at the end, what is the definition of inter-seismic phase? So you have here through time the velocity of a point located at the surface of the overriding plate. There is one time that is important in the life of this point is when the velocity is oriented seaward and landward. So this is this point when your velocity is negative, you are oriented to the west. So if we consider we are talking about the east velocity. And there is this time where your velocity becomes positive, and now the velocity is oriented toward the land. But this is not a good threshold to define that, because the velocity then continue to increase. So what is the good definition? I don't know, and I just here show you what can we learn with these two definitions. The first one is the instrumental definition. The GPS measurements precision is about 1 millimeter per year. So when your velocity vary less than 1 millimeter per year, you cannot discriminate it using GPS, which is actually which is currently the more precise way to measure the seismic cycle. And the other is more physical when this velocity has reached 90% of the maximum velocity. And so here are two different maps that show you the time after the earthquake. You are going from post-seismic to inter-seismic phase. When you're using the instrumental definition, you are in a near field, far from the trench, 10 years after the earthquake, in the inter-seismic motion, and it takes more time here in midfield when you need 60 years to reach this moment. And something that is really cool that you see with this other definition is completely the contrary. It's when you are in far field that you have the transition between post-seismic and inter-seismic that is later, and when you are close to the trench, it is earlier. So it comes from the fact that when you are close to the trench, you have in green here, your velocity is very high. You have at the end here of the cycle, seismic cycle, 18 millimeter per year. But when you are in far field, your maximum velocity is 1.1 millimeter per year. So 1.1 millimeter per year minus 1, it's very close to 0. So your time is very low. And at the contrary, if you're using the physical definition, you will need more time to reach this transition between inter-seismic and co-seismic. So just to say that we are interpreting the inter-seismic phase as a steady state, but from what I've shown you today, is there still a steady state in the plate deformation? It's that's the question. Do we have to use this word to consider what it's in between two earthquakes, and in between you have different physical processes that are playing a role, and so on? And why calling this part the pre-seismic when you are just right before the next earthquake? This is an open question, and I don't have obviously yet the answer. So here are my conclusions. The first is that the cyclic viscoelastic model, as I've shown you, approximate very well the realistic theory of slip along the subduction interface. We need this kind of viscous models to reproduce both the deformation right after an earthquake and 50 years after another one. And that viscoelastic model, of course, challenge our vision of the seismic cycle. For example, the definition of the inter-seismic phase, the transition between post-seismic and the seismic. And of course, all this work is possible if we have good data and good models, as I tried to show you today. So thank you for your attention.
Maybe one question just to clarify, what is the input of the model? You input sleep?
Yes.
Do you input also strength rate, like the loading, so that you get the long-term trend, or you decouple that and you just sum it afterwards so that you get this trend?
Good question. So just back to this slide.
Oh, the backslip, no, it's
yes, exactly.
Because on all the figures you are showing a trend in terms of, so for this you need something else than only the slip, right? If it was only the slip, you would just stabilize it.
Yeah. So how I model it. So in instead of your model, you apply a co-seismic slip distribution. So you have a displacement between two groups of nodes along the fault plane. And the thing is, you can mimicking the seismic cycle. You can doing something like that. The thing is, it costs lots of computation time. So to do it in terms of numerical approach, you impose your co-seismic slip at the beginning, and you let evolve your model for a very long period of time. And to retrieve this trend, so it is in all the map that I show you today. You consider that your station needs to go back from the quantity it moves during a given period of time. So you are.
Your model, I mean, you impose the slip.
Yes.
Normally, if it was only the slip that you were showing, you would just go back to a steady state of 0.
Yeah.
Well, in the very long term.
Completely, yeah.
But you are tilting it back.
You are considering that your long-term motion, so the trend you have, is the difference between 0 and what you get after a very long period of time. So that is your convergence motion. And to mimicking all the seismic cycles, we are just shifting the. So if you compute your viscoelastic deformation for 100 years, you just shift if your last earthquake occurred 50 years ago, you shift this curve by 50 years and you retrieve the right point.
But you need to make assumption on the slip of this past earthquake.
Yeah, in that case, in the red case, I assume that is always the same, always the same slip.
I have one question. So you have you made a huge effort to follow the geometry of the slab very well, but it seems to me that the thickness of the slab is constant.
Yes, completely.
And does that have any effect on the long-term seismic, or you neglect it because it doesn't have any effect?
So it's a really good question on the model. So now in this version 1.0, we have a constant thickness of all the geophysical layers. So the continental lithospheres, the slab, the oceanic lithosphere, and also the asthenosphere. So I make the assumption that the thickness is constant, and of course it has an impact. For example, the thickness of the continental lithosphere against the thickness of the slab has an impact on the time you are going seaward or landward when you are close to the coast. So it has an impact. But I made some tests, for example, to have a significant improvement of this line. So to put landward this inversion of sign, you have to, for example, double the size of your lithosphere. So to push back this limit of 20 kilometers, you need to increase your lithosphere of 50 kilometers. So at least that it has an impact, but not not as much you increase the size of your lithosphere, but it has an impact. Yeah, and maybe in the future we will try to make a model with lateral variation also of the lithosphere thickness. Or
question / comment. When you input, so the way you are doing that, like by matching the long term, means that when you impose slip on the non-planar interface, it will create some stresses that will be remnant because you impose slip on non-planar interface. This stress should accumulate over the cycles until maybe they are bound by plasticity or whatsoever. But here you are not taking that into the model. Right?
There is no plasticity, yes, in the.
So my question is, for like when you have a plate interface that is really curved and you put slip on it, you will increase change a lot the normal traction along this plate interface. And this is something that is increasing with the total accumulative slip. And the way you are doing that in your model, you are not really taking into account this stress concentration of the geometry because you just put one slip.
Yes.
And there is a way to implement that or to take that into account. That would be interesting because your interface is really non-planar and you have the flat.
But the first, maybe I can go back to this. The thing is that the seismogenic zone here, you are at this orange contour line here is 100 kilometer depth. So it means in my case, the slip I am imposing is close to the first 70 kilometers.
So one interface is slipping, even if it's creeping, it will change the stress in the interface.
Of course, yeah, of course. But the thing that I just want to say that there is no strong variation of the dip in the depth we are imposing the earthquakes.
Okay. But I think still, like for the time of the earthquake, yes, but over the long time, the whole interface is slipping. On this will create stress concentrations because of the non-planarity of the interface.
And this is my next project, working on plasticity. But yeah.
Okay. So I think I don't know if it has an effect or not.
It has, yes.
I hope for your next
it has.
project.
No impact, but it.
Any question online?
Is it possible to ask a question?
Yes, we are you.
Is it possible to ask a question?
Oui, yes. Yes.
Okay. I wonder, so it was a very great talk, Hugo. Thank you very much. When you show us that the viscoelastic cycle model is working to explain the GPS data at short time and in near field, in your model, you don't model the after slip part, whereas it's an important component in subduction zone. So including this after slip part for the near field and short time, it will change your viscoelastic parameter. So what do you think with respect to your general overview?
Yeah, you're completely right. In all the model that I've shown you today, there is only the viscoelastic relaxation of the asthenosphere that is playing a role in the deformation of the overriding plane. So there is no after slip. And of course, there is after sleep, and it plays, as you say, an important role for near field and mid field deformation. The first thing we can say is that if we want to make the things very clear, we have, of course, to take into account this after sleep. And if I go back to what I have in mind from the models from Emily, that for Maole tried to make a model without after sleep and with after sleep, it changed, of course, the value of the viscosity you have. But it changes not the magnitude, the order of magnitude of the viscosity. So instead of having, for example, 4 to 18 Pascal second, it was 3 to 18 Pascal second. So it changes, but it does not change the magnitude. That is the key actually of what I am showing you today, rather than having a really good fit in the near or in the midfield. But also after sleep can have an impact on far field deformation, because it's a slip on the interface, like the earthquakes, and it induces also its own viscoelastic relaxation. So it could be also interesting to look at it a bit more. Yes.
Yeah, it would also change your transient viscosity, actually. Not only the steady state one, I suppose. And if I may, I have another question. So this is a very great area to do the work you have done, because you have a good history of earthquake on a large part of the subduction, and you also have TPS that are very far away from the trench, without strong other tectonic processes that could affect them. But is there other place where you think that we can try to do the same kind of work? Because when we have not this idealized study area, it's more complicated to
No, you're right.
to constrain the viscosity rheology.
No, you're completely right. We have the chance in South America and in this part to have this great, to have a continent. If we in Indonesia or Japan, Japan, for example, you have very good coverage of the midfield deformation, and then you have the ocean, so you have nothing. You have some station in China from the work of a former student from Luz. There are some stations in China or Russia after the Tohoku earthquake that recorded some deformation, some viscoelastic deformation from the earthquakes. Recently, you have the Kamchatka earthquakes, but we have few stations. So again, and even northern introduction zone, this region is very well monitored, and even at the northern part of the Chilean subduction zone, it starts to be more difficult. So it's true that to compare to other places, it's not easy to test this hypothesis in other places. INSAR could be used, but the problem of INSAR is that the result we are discussing about millimeter per year of deformation. And INSAR in this way, from what I know, is not able to have this precision, this resolution we need. Yeah. No, it's a good point. Yeah.
And actually, as you said, for the moment you model the southern part of the Andean subduction, but if you I think you didn't try, so I'm not sure you will be able to answer, but if you use the parameter you found for this zone in the northern part of the Andean zone, what do you think? Because in your model, there is no lateral variation of your rheology, right? So do you think that in all South America, we should get a good answer with the rheology you find here, or do you think there is lateral variation of this rheology?
So the difficulty of northern Chile is that there is less GPS data in this region, in the far field region. For example, for the Iquique earthquake, 2014, you have only one station that is located at 1,000 kilometers from the trench. But this is a region where you have the trench is more distance to the coast. The other things we have, and that I am exploring in northern Chile, it's this problem of the sliver that we have, this third plate hypothesis that I presented you at the beginning, that we are maybe there is people that are discussing about the Liquiñe-Ofqui fault, if this fault have played a role during the Valdivia earthquake. So you have the problem of the sliver at the north, but maybe viscoelasticity will be able to add viscoelasticity in our models. Will be able to reconcile these two plates or four plate hypothesis. So yeah, I don't have the answer, obviously, but I'm looking. I will move northern to see what we can derive from these models.
Thank you.
Thank you.
Thank you. Thank you, Hugo.
Thank you.